Okay, good afternoon once more, ladies and gentlemen. I think we can start now. I hope more people will be able to join in later. So last time we met, we were looking at methods for solving linear systems of equations, that is numerical methods for solving linear systems of equations. So today, let's look at non-linear systems of equations. So we look at the last section in this chapter, non-linear systems of equations. Okay. So you remember that at the time we were looking at linear systems of equations, we're able to write the system in a general way or in a general form. So even in this case, we'll try to do that, but we'll just write these systems of equations in this way: f of x1, x2, and so on up to xn equal to 0. And we are going to have another equation, f2, x1, x2, and so on up to xn equal to 0. So we are going to have n equations in n unknowns. Okay, x1, x2, and so on up to xn is equal to 0. So this is the system of non-linear equations we are going to look at. Okay, so even in this case, we expect to have the number of equations equal to the number of variables, right? And to solve this system, we'll look at two methods. Okay. So these methods are somehow similar to the ones you looked at when we're looking at one variable case. So we'll look at the fixed point method and Newton's method. Okay, so these are the two methods that we're going to look at. So there will be more like generalizations of the one variable case that you considered. So we'll just look at a situation where we have n variables and n equations. We see how we can solve that. Okay, so straight away, let's look at the first method, the fixed point method. Okay, so Boniface, stop writing whatever you're writing on the board. Please, I'm able to tell who is writing on the board. Stop doing that. So we look at fixed point method. So this will be for the nonlinear system of equations. So straight away we'll look at one theorem. So this theorem is similar to the one you looked at when you're looking at one variable case. The only difference here is that we are looking at a situation where those functions are expressed in terms of n variables. So first let D be a collection of some constants. So we'll represent D by the following. So you have n variables here, x1, x2, and so on up to xn transpose, such that AI is less than or equal to xi, less than or equal to bi. Okay, so it will just be a collection of those constants, AI and bi. And then we will express those functions f1 up to fn in this form. For example, x1 equal to g1, x1, x2, and so on up to xn. And then x2 will also write it in this way. When you are looking at the one variable case, you saw that it's possible to write one equation in terms of one variable. Say I mean, in terms of that same x. And then you'll be able to make it the subject formula, and then from there you can apply the fixed point method. So we'll try to do something similar here. The only difference is that we'll look at n variables and n equations. So x2 can be expressed in that form up to xn. So let me wrap this part, okay. Up to xn, which will be expressed in this form, x1, x2, and so on up to xn. And then after doing this, we'll be able to write our function capital Gx, which will be in terms of these functions, g1, g2, and so on up to gn transpose. So of course, I'm just writing g1, g2, and up to gn. I'm not writing the variables on which these g are defined. So you will know that each gi is expressed in terms of x1, x2, up to xn. So we'll define our gx in that way. And then we will look at this as a function from d. Okay, let me say this be a function from d to Rn, where this d is the collection of those constants ai and bi. Then, if this gx is in d, then we'll say that this g has a fixed point in d. Okay, something similar to what we are looking at the time we are looking at the one variable case. So if gx is in d, then we'll say that g has a fixed point. Okay, and that fixed point will be the solution to that system that you have. Now let's talk about the other condition which will guarantee a unique fixed point. Okay, so in addition to this, we'll try to look at partial derivatives of each gi with respect to xj. If this absolute value is less than or equal to m over n, where m is less than 1, then we'll be able to see that this x will generate the following sequence: gxk minus 1. So we are going to have this sequence from k equal to 0 to infinity, which will be defined by this k equal to 0 to infinity, which will converge to a unique fixed point. So we'll let this unique fixed point be equal to p, and it is unique. And this unique fixed point is such that the error bound is as follows. So the error bound will be expressed in terms of the L infinity norm. So xk minus this unique point p, the L infinity norm of that x k minus p will be less than or equal to m to power k over 1 minus m, and then the L infinite norm of x1 minus x0, right? So this is the error bound. We can use it as a stopping criteria, but the challenge could be what is that p? Of course, I can be able to iterate and be able to get x1, x2, and so on, but I don't know the value to which it converges. Okay, if I've been given the exact solution, and then I can even find the error bound using the L infinite norm in this case. So what this theorem is telling you is that if, in summary, if this g, which will contain those functions from g1 up to gn, is in D, then I'll be able to see that g will have a fixed point. So this sequence will now be generated. And if partial derivatives of each gi with respect to xj is less than or equal to m over n, where m is some constant which is less than 1, then I'll say that that fixed point is unique. So that's what this theorem says. And like I mentioned, it is just a generalization of the one variable case. Okay, so let's look at an example and see how we can apply this theorem, and ultimately how we can apply the fixed point method to solve nonlinear systems of equations. So let me move on to the next board. Okay, so in this case, we are given the following systems of equations. So I won't write all the details of this example. You have it in your notes. I will just focus on how we'll be able to find the solution. So the first equation of this system is given by 3x1 minus cos x2 x3 minus 1 over 2 is equal to 0. Then I have x1 squared minus 81, then x2 plus 0.1 squared, and then plus sine x3 plus 1.06 is equal to 0. And the last equation is e to power minus x1 x2, then plus 20 x3 plus 10 pi minus 3 over 3 is equal to 0, right? So that's the system of equations that we are looking at. Okay, so we have been told that this system has a unique solution. So has a unique solution in D, which will be given by capital X equal to x1, x2, and so on up to xn. Transpose such that -1 is less than or equal to xi less than or equal to 1, right? And of course, I is is equal to 1, 2, and 3. Okay, so we want to show that this system of equations has a unique fixed point in that D, and we should be able to iterate using x naught equal to 0.1, 0.1, and minus 0.1. Okay, and then the stopping criterion we are going to use is the L infinity norm of xk minus xk minus 1, then divided by, I've run out of space here. So divided by the L infinite norm over xk. Oops, I can try something here. Okay, I'm sure we have gotten that part. And then this should be less than 10 to power negative 5. That's the stopping criterion we are going to use. Okay, I've run out of space there. But what I wanted to write is L infinite norm of xk minus 1 over L infinite norm of xk being less than 10 to power negative 5, right? So we are going to make xi the subject of the formula in each of these equations. So using the first equation, I'll make x1 the subject. So I'll make x1 the subject of the formula here. Using this equation, I'll make x2 the subject of the formula. Using this equation, I'll be able to make x3 the subject of the formula. And then those will be my functions gi, right? And then I'll be able to form that column vector, which will have functions g1, g2 up to g3. Okay, so let me move on to the next board and then see how we can do just that. Okay, so using equation 1, I can see that 3x1 will be on one side of the equation, and then I will take everything to the other side of the equation. So I'm going to have a cos x2 x3, then plus 1 over 2. So that from here, I'll be able to get x1, which will be equal to g1 of x1, x2, x3. And this will just be equal to cos x2, x3 plus 1 over 2. Right? I'll do the same thing. Using equation 2, I can have 81 x2 plus 0.1 squared to be equal to x1 squared plus sine x3 plus 1.06 here. So that from this equation, I can make x2, which will be g2 x1 x2 x3. And this will be equal to what? Making x to the subject of the formula here, I'm going to have a square root of, yes, Mr. Kanika, you have a question?
Yes, I think just a correction.
Okay.
On this one, the one for G2x, sign is supposed to be negative after the jump the equal sign.
Okay. Okay, let me take you to this board. So you can see that then this part is already negative. So it's like this is the part I've taken to the other side of the equation. So whatever remains it will be positive.
Okay, sir.
Is that okay? Okay.
Yes, it's all right.
Okay, so let's continue here. Oh yeah, we are on this board. So I'm going to have 1 over 81 here. Then I'm going to have x1 squared plus sine x3, then plus 1.06. Then the whole of this minus, so this one goes the other side, yes, minus 0.1. Right, so that this just reduces to 1 over 9, then square root over x1 squared plus sine x3, then plus 1.06, then minus 0.1. Okay, so we are going to do the same thing to the last equation. So from the last equation, I'm going to make x3 the subject of the formula. So definitely x3 will be equal to 1 over 20. Then I'm going to have negative e to power minus x1, x2, then minus 10 pi minus 3 over 3. And this will just be my G3, x1, x2, x3, right? Then after doing this, I want to show that this function G, which will contain now G1, G2, and G3 transpose, I want to show that this is in D, okay? So how will I be able to show that? So if each GI is in D, then I'll be able to show that even GX will be in D, right? So I just need to make sure that every GI that I have in there will be able to be contained in D. Or in other words, if I take absolute values of those, then they will be bounded by some value which is less than 1. Because remember, D has, let me delete this part. Remember, D has this xi less than or equal to 1. This is what we have been given in the question. Did I write this part? D, yes, we have this. So we just need to make sure that it is less than or equal to 1. So we'll start looking at each GI. For example, when I look at G1, so I'll just say G1 capital X, where capital X is X1, X2, up to X3. Okay, so I will take the absolute value of this. If this value is less than or equal to 1, then I'll know that it is contained in there. Okay, so let's do that. So the first GI that we have, let me say G1. The G1 that we have here is cos X2, X3 plus 1 over 2. So I'll take the absolute value of that. So absolute value of 1 over 3 cos X2, X3. Then what else do I have here? Let me take you to this. Or actually, this is supposed to be 1 over 6, right? Because I'm dividing by 2. So this, by 3, so it will now be 6. Sorry, I think I made that mistake. So this is supposed to be 1 over 3 when I simplify. So this will be 1 over 3, then 1 over 6 there. Okay, I forgot to divide by 3 throughout. Okay, so that's the function we're going to get. Then plus 1 over 6. So we'll be able to see that this will be less than or equal to 1 over 2. Because I know that x2, x3 there, x1, x2, and x3, they are all in that D, and D is between -1 and 1, right? So whatever combination I have there, I know that cosine is less than or equal to 1. And remember that in this case, you're considering cosine and sine in radians. So you can easily see that this would be less than or equal to 1. 1 over 2. Okay, so I'll do the same to G2x. In this case, G2x, let me take you to the previous board. What do I have? G2x. Okay, I have this particular function. So that's what I'm going to consider. Absolute value of 1 over 9 times the square root over x1 squared plus sine x3 plus 1.06, then minus 0.1. So you'll be able to see that for all those values that you have in D, this expression will be positive. Okay, it will be positive. So this will just be less than. So I can consider 1 at the far end there, those endpoints. So I can consider -1. The one which will have, the value I'm going to get for x3 equal to -1. This one will make the sign here to be negative because sine is an odd function. So that value will be less than the one I'm going to get when I consider x3 to be equal to 1. Right? So that will be my maximum value. So this will be the same as 1, or this will be less than 1 over 9, then square root over 1 plus, so it's like I'm taking side x1 to be equal to 1, x3 to be equal to 1, and then I'll be able to get this plus 1.06, then minus 0.1. If you evaluate this, you'll be able to see that it will be less than 0.09, right? And like I mentioned, this cosine or sine are in radians. So if you use a calculator which is in the degrees mode, you are going to get a value different from the values that I got there. So you need to make sure that you change the mode of your calculator. Similarly, we are going to find absolute value of G3. And this will just be equal to G3, we got -1 over 20 e to power minus x1, x2. No, it's x1, x2, then minus 10 pi minus 3 over 60. Okay, so that's what we got for G3. Okay, when we expand, that's what we are going to get here. Okay, G3 is given by that. So let me take you to this board now, and we'll be able to see that the negative will disappear when I take absolute values. So this will just be equal to what? The combination of x1 and x2, where x1 and x2 are in D from -1 to 1. Okay, so this will be maximum when x1 is -1 or x2 is +1. So I need to have this part to be positive, and that can happen if the signs are alternating for those two. I mean, for that product, x1 times x2. So that can happen when, for example, x1 to be equal to -1 and x2 to be equal to 1. So that this product is just equal to 1. If I have a negative value in there, then that value will be smaller than this one that I'm going to get when I have the product to be equal to 1. So looking at that, I'll be able to see that the maximum would be at 1/20, then e to power 1, then plus this number 10 pi minus 3/60. Right? And you'll be able to see that this, if you use your calculator, it will be less than 0.61. Okay? So what we have seen is that all the absolute values of xi are less than 1. So it means by doing that, then we'll be able to show that, or we'll be able to conclude that each gi is in that interval. So in other words, it will be in D. Okay, so from here it means g of x is in D. So according to the first part of that theorem, if gx is in D, then it means this g has a fixed point. But we do not know if it is a unique fixed point or not. For it to have a unique fixed point, then this other condition must be satisfied. Partial of gi with respect to xj should be less than or equal to m/n, where m is less than 1. So that's the next thing we need to do. Okay?
Sorry, sir.
Yes, sir.
I think I'm behind on how you are picking the GI that you are substituting in those G of 1 and G of 2 and G of 3.
Okay, maybe joined in late. Remember, we have these equations. I earlier on explained that from equation 1, we are going to make x1 the subject. This, from equation 2, we are going to make x2 the subject of the formula. From equation 3, we are going to make x3 the subject of the formula. So that
yeah, I'm okay on that part. Now the area where you were substituting the x1, like in the first equation of the absolute value of g of 1, the
G1.
end part there shows, yes, g1. The end part shows that it is less than or equal to 1/2.
Okay.
Are you able to see that? Yes. So I'm lost where you're picking how you are getting the x2 and x3. Like, which values were you picking?
Okay, remember, D is given by this. Oh, sorry. D is given by this, right? So
yes.
x2 and x3 are between -1 and 1.
Yeah, so within that range, which values exactly were you picking?
So I'll pick those which will make this to be how can I put it? So I'll pick those which will make this to be a maximum. Of course, I know that x2, x3, for whatever value I have there, this is less than or equal to 1. We know that, right?
Yes.
Yes. So I can even use that and even the triangle inequality.
Okay. So you're just picking the value.
Yes. So this cos x2, x3 is less than or equal to 1, right? So I'm going to have 1/3 plus 1/6. 1/3 plus 1/6 will give us what?
Okay, so in short, you're just picking the value that would make the absolute value to be greater than or less than what? To be greater, isn't it?
Yeah, definitely. So I need to look at the maximum value that I'll be able to get for that G1x absolute value of that. If I
Oh,
got,
all
for
right.
example, if for example, I got this part, if I got this part to be maybe 1.52, then I'll say that this part is not in D, right? Because in D, I only have values between -1 and 1.
Okay, I think I get it from there. Thank you.
Okay, I'll come. Okay, let me get that. Okay, so I was saying our next task is to show that this condition is also satisfied. Then if it is satisfied, then we'll be able to say that this has a unique fixed point, not just any fixed point, but a unique fixed point. So remember I have G1 given by, G1 is given by 1/3 cos x2 x3 then plus 1/6. That's what I have. So I just need to find the partial derivatives of G1 with respect to x1, x2, and x3. So with respect to x1, you'll be able to see that this will be equal to 0, right? Then partial of G1 with respect to x2, what will I be able to get? So there will be a negative of x3, then sine x2, x3, then divided by 3, right? Is that okay, ladies and gentlemen? So that's what we're going to get. So I'll be taking absolute values of these. So of course, this one will be equal to 0. Then I'll take absolute value of that. And taking the absolute value of this will just be equal to what? If I want, I can even say this is just less than or equal to 1/2. Of course, I can even say this is less than or equal to 1. Okay, if I want to be more precise, then I'll use those values that I have in D, right? So this should be less than or equal to, if I take absolute values, then of course, the one with, the negative part will disappear. So I'm going to have 1/3 here, and then I'll pick sine 1. So this will happen when